I am very happy to be here. I have fond memories of previous visits to this institute, and I'm very happy to be back again. This will be an historical talk. Portions of it will be found in greater detail in this book, recently published. It will be understood that in selecting topics for this presentation, I had to make many decisions. Which topics shall I choose for their fundamental interest, for their edifying example, or for other human interest aspects? And because of that, I have decided that I will present these topics in segments, after which of each I shall stop briefly to discover whether you have opinions on whether I chose the right topic and the right emphasis within the topic. But you will understand that I have to keep this short because I've chosen quite a bit of material to present. So, first, how did we come upon the notion that the universe is homogeneous and isotropic on the large-scale average, no center, no edge, no preferred direction? I believe the story appropriately begins with Newton, who remarked that I may hold a bucket of water and by looking at its surface determine, am I rotating? If so, the curved surface of the bucket is curved. If not rotating, the surface of the bucket is flat. I need not consult the distant stars to determine this. I have made an absolute determination of rotation. Mach, as well as others in the late 19th century, objected that this may not be the whole story. It was that very provocative remark of Mach that I'd like to bring to your attention. No one is competent to say how the experiment would turn out if the size of the vessel increased in thickness and mass until they were ultimately several leagues thick. The experiment is to be done. It has been done, very perceptive, lens tearing. We recall that Einstein was influenced by Mach's consideration in developing his theory of gravity, general relativity. That in 1917, Einstein introduced his great paper that started the modern theory of cosmology, introducing the notion of a homogeneous isotropic universe to which one applies general relativity theory. In that paper, he argues against the notion that we live in an island universe of stars, what we would now call a galaxy. For he said, if we apply Boltzmann's law to an island universe of stars, and if we agree that the density at some large radius is zero, then in an isothermal gas sphere, the density is everywhere zero. I do not follow that argument. I don't know why we couldn't have had a universe with one isothermal gas sphere, the density going to zero at arbitrarily large distances, asymptotically as 1 over r squared. I think we see what Einstein was really objecting to in a comment in 1922. He realized that one can have a solution to general relativity theory that is an island universe of stars, outside of which space is asymptotically flat. That island universe may be a galaxy that is rotating, but rotating relative to what? Einstein says that if the universe were constructed on this plan, then Mach was wholly wrong in his thought that inertia, as well as gravity, depends on a kind of mutual interaction between bodies. There is the theory, therefore. To Einstein, the only universe that makes sense is one that is homogeneous, perhaps closed. I don't know whether he would object it to open, but homogeneity needed to satisfy his interpretation of Mach's principle at that time. Well, that's my first segment. Good, we will carry on. That was pretty non-controversial, perhaps a little more controversial. The observational side. It is not recorded that Einstein consulted Eddington on this subject. He certainly did talk to the astronomers in Leiden, who knew perfectly well that we live in an island universe of stars, the Kapteyn universe. Here, in this book by Eddington, one sees the title, The Structure of the Universe. To Eddington, the universe was our Milky Way galaxy. Star count showed that it is an island universe, quite contrary to Einstein. The shape is about right, our position not right, no account taken of obscuration. That would be useful. Well, am I going to push the wrong button by mistake? Well, you never know. 1914. The war certainly got in the way, but he was talking to astronomers in Leiden. He somehow royally ignored them. This is not a logical universe. Eddington and others were quite aware of the spiral nebulae, and they were quite willing to accept that these might be other island universes of stars. But it was very clear to the astronomers of that day that these nebulae are by no means uniformly distributed. Here, 1922, Charlier, a map, full sky, plane of the Milky Way along here, the nebulae. It looked to Charlier very explicitly not as a homogeneous universe, but as a fractal, as we would say, or as he would say, a clustering hierarchy. Einstein was aware of this proposal, dismissed it as theoretically excluded. 10 years later, astronomers have convinced themselves that the spiral nebulae really are other island universes of stars. They were now convinced that the absence of stars along the plane of the Milky Way, this curve in this projection of the whole sky, and that the view out the poles is quite reasonably clear, and that the distribution of galaxies is very inhomogeneous, quite different from Einstein's vision. This situation did not improve until the 1960s. During that time, Einstein's universe was taught. I learned it as a graduate student, but the basis for it was quite questionable. That situation changed with the development of new technology, in particular, radio astronomy. Perhaps some of you of a certain age will recognize that this is a transparent sheet to be used in overhead projectors. Those were the days. You see it's yellowed, it's dirty, it's messy. But what it shows, first you must ignore the hole in the center. The instrument can't reach it. You must ignore the distribution around Cas A because that bright source confuses the instrument. And what do you see elsewhere? Einstein's vision. This, along with the isotropy of the X-gamma ray backgrounds, were the first, to me, compelling evidence that we might live in Einstein's universe. You could ask me at those times when I was showing this in the late 60s, so how do you know those radio sources are extragalactic? I could only answer, we know some are. And if many were galactic, why in the world are they so isotropically distributed across this half of the sky? We have now beginning of tangible evidence. It took another, 40 years after this to get a whole sky map of optically or infrared selected galaxies. Here again, full sky, 2-micron survey of galaxies. At that longer wavelength, the obscuration in the galaxy is not so important. Here is the plane of the galaxy. In this projection, you see missing galaxies there. Elsewhere, you see the large-scale texture of our universe. Indeed, very clumpy, as people had known for a half a century at least. But the clumps scattered about, as if we were seeing the approach to a homogeneous universe. And well, here the microwave sky, here the plane of the Milky Way, and here fluctuations of a part in 10 to the 5th, which in the standard model tell us that the universe is homogeneous to a part in 10 to the 5th on the scale of the Hubble length. Dramatic. So we come to the question, was Einstein right for the right reason? I hope you understand that I have time to take nothing away from Einstein's great genius and creativity to observe that he didn't give much thought to his static universe. Our physics is not well suited to a static eternal universe. Consider entropy. Consider that stars surely cannot shine forever unless you create energy. And if you create energy, you're going to have to get rid of it, and you're going to have to get rid of the dead stars, too, if they evolve. Consider also that Einstein's universe is in a point of unstable equilibrium. Disturb it, it will contract or expand. Consider also that he came to think that lambda, which we feel is such an obvious part of general relativity theory, was an ugly part and that we should ignore it. You recall the famous statement he is quoted as saying, I don't know whether he said it because he was not a modest person, my biggest blunder. Would Einstein have accused himself of a blunder? Well, perhaps. If so, I can only speculate that the blunder was he didn't listen to his theory and recognize that the universe must expand or contract. I come to expansion and contraction in a moment, but first let me pause. I should remark that in the 1970s, the people at last began to question the assumption of homogeneity. I believe it was Gerard de Vaucouleurs who led the charge there. He was right to ask the question, certainly, is the universe homogeneous in the large scale? But he was a little late. We already had isotropy of the radiation backgrounds and of radio sources. It was an uphill battle. Curiously, the battle took a long time to be resolved, but it is resolved. Redshift distance relation, one transparency only to remind you that we first had a linear relation between redshift and distance in 1929 with a publication by Hubble of his recession velocities, distances in a linear scale. Here, 0 redshift, 0 velocity. Distances to individual galaxies determined by observations of their stars or star clusters. This is very difficult because you have to observe stars. Here, a great extension of his redshift distance relation by looking at relative apparent magnitudes of brightest galaxies in clusters. These brightest galaxies are a fairly uniform set, and so ratios of distances follow directly from ratios of luminosities. And he was able to extend this by 1936 with Hubble to redshift 10%. Recession velocity 10% of the velocity of light. Spectacular, 1936. I was 1 year old, and they were looking to redshift 0.1. It took from 1936 to 2000, what is that, 70 years? We have the next factor of 10. So I emphasize in particular 1929 because I want to go on to the next step, but I will try to remind myself, have I stepped? I see acquiescence. Who found the Big Bang? To me, it was not the Russian Friedman. He had the deep misfortune to have found it too soon. To me, a discovery in the natural sciences is a connection between theory and observation. A mathematical solution, to me, can be very impressive, but it's not physics. The physics comes with the phenomena. And to me, it was the Belgian, Georges Lemaitre, who made the connection. He was fortunate to live at just the right time. In 1925, was it, he visited the US to do a doctoral degree at MIT. He heard Hubble lecture on his research on the galaxies. We don't know how much Hubble knew then about the redshift distance relation, but we have a, I should notice that here is the last part of a very familiar derivation of Hubble's law. Here is the bottom line. Recession velocity is CR times R dot over R. That's Hubble, R dot over R is Hubble's constant. This is a derivation of the linear redshift distance relation. I put the footnote here from his 1927 paper. Well, first, it's amusing to pause to consider he had Hubble's constant as 575, 3 significant figures, kilometers per second per megaparsec. Almost exactly the same as what Hubble had in 1929. He certainly, it was based on Hubble's earlier published absolute magnitudes of a few galaxies. We don't know much more than that about how it is that Lemaitre got so close. More important, some have tried to put in place a relation between redshift and distance, have obtained only a very weak correlation. I conclude from that that it's unlikely that Lemaitre was guided by a known redshift distance relation in his derivation. That is further confirmed by the fact that when at last Eddington recognized the importance of this 1927 paper and arranged to have it republished in monthly notices in 1931, this footnote was removed. Because, of course, someone had at last put forth a correlation that was strong, not weak. But I think it is fascinating to notice that Lemaitre was entirely entitled to have claimed that he predicted the linear distance redshift relation. But to have said that would have been quite out of character with all I know about this individual. You will notice that I'm leaving out important things. Where is the steady state theory? I will not talk about it until the very end. I go directly to the hot Big Bang. The first important step, you may argue again, was pure mathematics, but it turned out to be very perceptive. Richard Tolman, MIT, observed that in an expanding universe that is filled with thermal blackbody radiation, the expansion cools the radiation but keeps its thermal spectrum. There is no need for the traditional grain of dust to force relaxation to statistical equilibrium. Once the radiation is in thermal equilibrium, the expansion will only cool it, not destroy its thermal spectrum. It was 10 years after that, approximately, after the Second World War, when George Gamow turned his attention to this result of Tolman. Some of you of an extreme certain age may remember these images that appeared in newspaper commentaries. This is the hydrogen bomb, the super bomb. In those days, I wasn't at all sure the world would be still here at this time. Somehow, I think through more luck than good management, we are here. This is going to be important in a moment as I tell you about one of the early papers, well recognized, the famous alpha beta gamma paper, in which beta was involuntarily introduced in order to complete the symmetry, pointing out something that was of deep and lasting interest, that the abundances of the elements as a function of atomic number vary inversely as the hot neutron capture cross-section. A result that has been transferred to the R-press process in stars. I don't know how closely it has been translated. When I look through the literature, I don't see credit to alpha and beta, alpha and Gamow for introducing the R process, but it seems to me they did. They also introduced a real problem. For you notice that they knew about the neutron capture cross-sections that came out of the work that made that bomb. And they knew the value of sigma v around this number for hot neutrons. You want sigma v to be the reciprocal of nt in order that you will burn an appreciable amount of hydrogen to heavy elements, but don't go all the way. Hydrogen is still the most abundant element. Therefore, you want sigma v to be on the order of the reciprocal of nt. You know then that at the time of heavy element buildup, the expansion time times the number density ought to be about this number. Alpha and Gamow assumed a cold Big Bang, where the mass density is the number density of protons times their mass. You tell me the mass density, I'll tell you the expansion time, because in those early days, space curvature and lambda couldn't be important. The expansion time times squared times the number density in general relativity theory works out to this number, 10 to the 30th seconds per cubic centimeter. I have the units slightly wrong here, cubic centimeters. But now take this number and this number, you get an expansion time of 10 to the 10th seconds, 1,000 years. Where in the world could the neutrons have come from? That expansion time is enormous compared to the lifetime of a neutron. This theory doesn't make any sense. That was first recognized, at least in print, by Alpher in his thesis. I don't know of any other article in print in those days that pointed out that alpha, beta, gamma were totally made no sense. And Gamow never admitted it, but Gamow pointed out the solution. Go to a hot Big Bang. They wanted a hot Big Bang because they wanted to avoid the strong resonances of slow neutrons, which would have quite messed up the inverse relation of capture cross-section and abundance. So go to a hot universe. Then Gamow realized full well that, well, first for this reaction, photoproduction of deuterium, sigma v is 10 to the minus 20. Well, a tenth of Hughes's general number for the general trend, but that's all right. This is the order of magnitude. That is to say, we want NT to be around 10 to the 20th cubic centimeters here, second per cubic centimeter. He also was fully aware that at very high temperature, the reverse reaction will destroy deuterium as fast as it's formed, but that at a temperature of about 10 to the 9th degrees, finally the radiation is too soft to be able to photo-dissociate deuterium. Deuterium can start to build up and make heavier elements. So the critical time when element buildup can commence is at temperature 10 to the 9th. Knowing a temperature in a radiation-dominated universe, you know the mass density, so you know the expansion time is about 200 seconds. Put 200 seconds into here, and you find a number density of about 10 to the 18th per cubic centimeter. The first check of consistency is that this mass density is well below that of the radiation at that time, so the story makes sense. It was Alpher and Herman, immediately following Gamow's paper, who took the next critical state. The present number density is something like 10 to the minus 6 per cubic centimeter. From 10 to the minus 6 to 10 to the 18th is 10 to the 24. The temperature goes inversely. Temperature goes as the cube root of the number density. The cube root of 10 to the 24 is 10 to the 8th. And 10 to the 9th degrees divided by 10 to the 8th is cooling to present temperature of 10 degrees Kelvin. That could not be a precision computation because the mass density in the universe was uncertain by 2 orders of magnitude at that time. But it was in the ballpark. It was in the ballpark of what later was found. So I come to the end of that episode. I see acquiescence. To determine that this hot Big Bang theory is right, you need predictions that may be tested. In particular, it was recognized from the first by Lemaitre that if the universe did expand from a hot, his primeval atom, or hot Big Bang, it has to have left fossils. There were 2 fossils in the early days to be determined, to be discovered. The first, the light elements that Alpher and Gamow were discussing, remnants of the hot Big Bang. The first recognition of a fossil from the hot Big Bang was made by Don Osterbrock. He recalls that in 1953, he attended a summer school at the University of Michigan. This was a famous series of lectures in physics in summer schools at Michigan, organized by Gutschmidt, right? And in that lecture, he heard Gamow, who described his ideas about the hot Big Bang, including helium production. Don records that he was very impressed by Gamow and his ideas, a sparkling person, lovely ideas. I think it was Jeff Burbidge who may have been the first to note that there's something interesting about the abundance of helium in the Milky Way, that there is more helium than could be accounted for by the burning of the known stars. That is to say, where did the helium come from? Osterbrock was certainly aware of this, and he and Jack Rogerson added to the evidence that the older stars have high helium. What in the world, where could this high helium have come from? Their remark, recorded here, this high helium abundance in old stars that have low heavy element abundance. The elements were being made, but the helium was already there, readily understood on the explosive formation picture, reference to Gamow. Here I add a personal recollection. My first paper in astronomy was a computation of the structure of the planet Jupiter. I needed helium to make the numbers come out right. I consulted Martin Schwarzschild, who pointed me to this paper. I referred to that paper in my paper on Jupiter. But at the time, I knew practically nothing about cosmology aside from the most elementary assumption, homogeneity, the analytic solution. The words explosive picture meant nothing to me. but it must be recorded. Here was a connection between theory and observation. And I just paused to remind you, as I'll come back to in a little more detail later, that here is a power spectrum of the variation of the microwave background temperature across the sky. Here, wave number, the analog on the sky, reciprocal of angular scale increasing to the left. Here, power spectrum after having taken the square root. No, power spectrum normalized to variance per logarithmic interval of angle. And notice that the predictions of a now standard theory depended on the mass density in baryons. Notice that you can fit the measurements very well, but that this is curve fitting. You have a curve whose shape can be adjusted, choose parameters so as to fit the measured points. Have you done more than curve fitting? Very difficult to decide, but you have a number which can be compared to the old Alford-Gamow theory of light element production, which predicts that at the onset of element formation, the higher the baryon density, the more deuterium is burned out to helium. And so there is an inverse correlation between deuterium abundance residual and baryon mass density when the temperature was 10 to the 10th, or knowing the present mass density, present temperature of the present mass density. Here, observations, I think these are from David Tytler. Here, a graph from Gary Steigman. Here, the inverse correlation of deuterium with baryon mass density increasing to the right. Here, a fit baryon mass density. Here, the glorious triumph of physical science. These two numbers obtained from looking at the universe in very different directions gave the same number. That's the magic of a developing good science. So we go on now. I think the first detection, though not recognition of significance, was McKellar. This is a copy of an old copy of that paper that was in my files. And archaeological interests, we need some detective work. This is my handwriting. This is David Wilkinson's handwriting. I have no idea what he was doing. Why is he playing with this number? This is the correct number. But anyway, around 2.3 degrees of curiously surprising spin temperature of cyanogen in its ground state and first rotationally excited state. The ratio of abundance is measured by absorption to a common state. Significance not recognized for many years. I take a moment just to review some pleasant history. Here, a temporary building built during the beginning of the Second World War for war research, in particular radar at the MIT campus. Here, Ray Weiss, you'll see him again pointing to that building. Alas, that building, it was built as a temporary building in 1940. They've gone and torn it down recently. I mean, nothing is sacred. Here is a photograph of my teacher, Bob Dickey, holding what he termed a shaggy dog. Here is one of his inventions during the war, a microwave radiometer, sensitive to microwave radiation. You see the horn. We'll see some more horns. Here, a view from that rooftop of Cambridge, which at the time was an industrial city with factories, with chimneys, some of which were warm. Here are scans across the horizon by this radiometer. The angle is distance from the zenith. At 75 degrees, the radiometer sees nothing. The sky is pretty smooth. As you approach the horizon, you start to see temperature is increasing downward, you notice, warm chimneys. This is just the thing to look for thermal radiation. And furthermore, here is a paper from 1946. They looked at the sky. They measured radiation from the sky. That was important because during the war, there was a great pressure to go to shorter wavelength radar. But as you go to shorter wavelength radar, you encounter absorption. That's greatly slowed progress. His radiometer was used to explore that absorption, find collisional broadening in the atmosphere. And it is also found that there is very little, less than 20 degrees, radiation from cosmic matter at microwave wavelengths. He was not thinking here about the Big Bang. He was only doing the good physical thing of asking, what's out there? And remarking no more than 20 degrees of thermal radiation at that wavelength. People have asked themselves, could Dickey or someone else in the 1940s, early 1950s have extended this limit down a factor of 10 and got a detection? The smart money, I understand, is that yes, they could have done it. If you really, really thought it was important, you would pour money and effort into it and you could do it. They had the sensitivity. But it didn't occur to anyone. 10 years later, is that right? Yes. No. 56. No, that's right. Yeah. Well, a little more than 10 years later, the first detection. There have been in the literature many claims to previous detections, again, not recognized. I went through all of those with all the care I could muster with the help of Lyman Page. I could not substantiate any of them. As far as I know, this is the first instrument to detect this radiation. 1959, a horn reflector, radiation bounces off the curved surface here and into the instrument. There was a time when objects of this sort were common on telephone poles in the United States, maybe here with the horn pointed up, the reflector pointing the beam horizontally, designed to have excellent rejection of background, of radiation coming in from below. Excellent rejection. That's important because, it's interesting to notice, see the wood beams. This is a very informal construction. It could only scan the sky in one direction. You could rotate this horn, but you couldn't scan in azimuth. Here is, though, something very sophisticated inside that small shed, a maser, low noise traveling wave maser amplifier, and here indicated contributions to the noise received by components along the way. These numbers added up to the noise received. That, however, was slightly suspicious because Bob Wilson points out to me this 2 degrees is a vast overestimate. These horns are much more efficient than that at eliminating backlobe pickup. That should be close to maybe a half a degree. He points out also that the noise assigned to the traveling wave amplifier was slightly overestimated compared to what the engineers would tell them, such that they had an anomaly of about 3 degrees. This anomaly was known within the Bell Telephone Laboratory system and a source of great annoyance to Arnold Penzias and Bob Wilson, who wished to use another version of this horn reflector system. You see this one much more sophisticated for astronomy, but they were deeply frustrated by the fact that they could not make the sums add up for the noise, an anomaly. They are to be credited for the fact that they stuck with this anomaly. They did all kinds of experiments to try to explain it, including in particular going to Dickey switching against a cold load. And the second thing for which they are to be credited is they kept complaining until finally, what am I doing? Oh, what am I doing? Until finally, the complaints reached Bernie Burke, who, in the middle here, who said, you ought to call Princeton. They did, and they learned about an experiment going on at Princeton. Bob had finally realized that it would be amusing to look for radiation from a hot Big Bang, and he had persuaded these 2 young guys, David Wilkinson. Peter Roll, you can just see his plaid shirt in the background, a Dickey radiometer built for the purpose of finding this radiation. And the connection was made. Suddenly we had a candidate for radiation, another fossil from the hot Big Bang. Here is the Penzias and Wilson discovery point. Here is Princeton that came in shortly after. By early 1966, we had these 2 points and things looked kind of promising. Clearly, there was a new form of radiation, not something that could be ascribed to galaxies and worth exploring. But certainly, well, let us notice that by the end of 1960, the long wavelength part of the spectrum had been pretty thoroughly mapped. We see that the community was ready to measure this radiation once someone thought of doing it. The technology was all in place. very quickly. This part of the spectrum measured. Here is the cyanogen interstellar absorption line. Here are upper limits and maybe a detection at shorter wavelength. Getting over the peak and down the back was enormously challenging. Took 20 years from the time of this slide. During that time, we had a series of measurements that all showed an anomaly. One could be slightly suspicious of the anomaly because it was different in each experiment. The anomaly certainly persuaded me not to work on microwave background anisotropy, because if the anomaly is real, it means that the radiation has been disturbed by explosions, radiation from galaxies, whatever, and its spatial distribution will then teach us a lot about explosions, but not much about the early universe. That is not a complaint. People were doing what scientists should do. They were working very hard to try to measure this spectrum and to see whether there really is an anomaly. So 20 years after this, we at last had these spectacular demonstrations of a thermal spectrum. Gorgeous. Because it is not well known, the two independent experiments produced this result within 2 months of each other. I choose to remind you of a few points of history. That the one group, consisting of Herb Gush at the University of British Columbia in Canada, had already in 1974, that was 16 years earlier, presented the result of a rocket flight using interferometer, that is essentially the design that was eventually successful. The flight was fine, but contamination by radiation from the Earth. He didn't know enough about antenna theory. That, a year later, we had the first report to NASA of a proposal for what became the COBE satellite. Here's John Mather, Pat Thaddeus, Ray Weiss, you saw his photograph, Dirk Muller, Dave Wilkinson, Mike Hauser, and Rob Silverberg from Goddard Space Flight Center, 1974, 16 years or so later. And here are the COBE team, John Mather, leader of this project. You got to admire his courage. He was a raw postdoc with only a few publications when he took on this job. 15-year job, at the end of which you have your precious experiment on top of a bomb. When you light the bomb and hope the energy is directed. I mean, that takes courage. It worked, and he's now a Nobel laureate. Here is George Smoot for the anisotropy detection I'll be mentioning later. Here is the other group, Herb Gush at the University of British Columbia. And by this time, he had picked up a group, these two people, Mark Halperin and Ed Wishnow. I have now to confess that whenever I see this image, I have to smile. And to ask myself, and I can't resist asking you, if you didn't know these people had done something great, if all you had to judge them by was this photograph, would it inspire confidence? Which of course explains why I shouldn't ask you such questions. Well, here is the spectrum now in modern glorious detail. Pause to consider 3 orders of magnitude in wavelength, all kinds of methods of measuring it, glorious consistency, wonderfully close to pure thermal blackbody radiation. The universe as it is now is transparent at these wavelengths. You know that because you can see distant radio sources at these wavelengths. The universe as it is now, therefore, is quite incapable of producing this spectrum by thermal relaxation. This is close to tangible evidence that the universe has evolved from a state that was much denser and hotter and capable of relaxing to equilibrium. Of course, the universe is not now in equilibrium, and there are hot sources that somewhat perturb this spectrum, but there's a lot of energy in this radiation, the perturbation quite small. A glorious advance, and quite worthy of a Nobel Prize. And a gift from nature. A gift from nature. Microwave, the development of the cold dark matter model, I think, traces back to the late 60s when we were doing the obvious things. The early universe, the baryons are thermally ionized. The plasma interacts strongly with the radiation by electron scattering. The result is that the radiation plasma acts like a fluid that is viscous. This fluid, under the assumption of homogeneity, starts smoothly distributed. If you want to make structure, you have to put in small irregularities. Gravity will force those irregularities to grow. The pressure of the fluid will cause the irregular growth to start oscillating. At redshift about 1,000, matter recombines, releases the radiation, and leaves an irregular distribution of matter with a pattern that can be computed. First steps, well, Joe Silk analyzed the viscous damping of this matter radiation fluid. I did the same thing and presented it at a Texas conference and then submitted as requested the contribution in which I explained this calculation, then forgot about it for many years until I noticed that that proceedings never did appear. So those are the breaks. It's part of science. Sinyaev and Zeldovich pushed this fluid picture further, got oscillations. Jerry, you and I took the next step and said, let's describe this radiation as it is. Let's do radiative transfer of radiation and matter in essentially the modern calculation. We got the modern bumps and wiggles in the power spectrum of matter and radiation. Here I take as a representative the next big step. Let's introduce non-baryonic matter. Before this, people had been discussing the possibility that there might be what we now term dark matter, George Chapline among others. But there was not much interest in it until in the early 1980s, the Russians announced the possible demonstration that neutrinos of electron type have a mass up around, I don't know what it was, does it say? Enough to make an interesting contribution to the mass density of the universe. It triggered enormous excitement that didn't die when the neutrino mass died, because once you start considering the idea of non-baryonic matter, the theorists offer you a cornucopia of other possibilities for the nature of that dark matter. Here, another interesting remark illustrating the way science goes. Dave Wilkinson with his students, his colleague Steve Bond, another junior faculty member. No, by that time, he was at Haverford. Ed Cheng, a student of Wilkinson, 1981. They thought they had detected the quadrupole anisotropy at a very big value. That was reinforced by measurements at the Canary Islands that seemed to indicate a similarly large quadrupole anisotropy. I, as an obedient theorist, immediately made a theory of that anisotropy. It was a beauty, a really lovely theory, but soon the anisotropy was withdrawn, new, much tighter limits put on, and I, as a good theorist, dropped that theory and made another, lambda CDM. I got the right answer. It shows you how theory and observation do interact, even in cosmology. Here was the first calculation, I believe, for the higher multiple moments. Angular scale increasing to the left, power spectrum, as I mentioned before, plotted vertically. Again, this is the variance per logarithmic interval of angular scale. Now, I show this to make another point, adiabatic isocurvature. In those days, we had lots of freedom to speculate about how the universe evolved. How did structure form? What are initial conditions, for example? What are the main dynamical actors? I remark in an illustration of this simply, an article by Joe Silk and me entitled Cosmic Book of Phenomena. Book in the English term meaning list of odds, bets placed. I ask you not to attempt to read anything on this archaic diagram, except to notice there are lots of phenomena that bear on this notion. How did structure form in the expanding universe? And there were lots of ideas on how that structure formation could have been triggered. Cosmic strings, exploding superconducting cosmic strings, isocurvature perturbations, adiabatic perturbations, pure baryonic, dark matter. We had all these choices. We had very few constraints on them that could be easily interpreted. Lots of phenomena, but difficult to know what is going on. And that required, whoops, did I miss something? No. That required measurements that are easily interpreted. So I pause. Is it agreed that in the, well, let's see, in 1990, we had all kinds of options for how structure formed in the universe, and therefore what the anisotropy spectrum of the microwave radiation would be. It was not, the present theory was not handed to us on a platter. We had it, but we had lots of other options. I think that's important to remember.
We certainly agree, because those that were looking for it had no clue where to look. So
yes.
we basically went where the telescope led us.
Right. Go where you can make the measurement. So let us go down that path, memory lane. Here, for personal reasons, I am charmed to present this, a clipping from a newspaper article, Denver Post, July 24th, 1967, page 13. Harold and Thelma Wilkinson, Dave Wilkinson's mother and father, happened upon this article at the Brass Lantern restaurant in Kimball, Nebraska, while traveling. He made his parents very proud. With him is a microwave radiation horn and Bruce Partridge. He and Bruce and Dave produced a bound on the anisotropy of the microwave radiation. It is plotted here in the first of a series of figures that you can find in that book, and they're worth the price. They were made by Lyman Page, and they document progress in measuring the anisotropy of the microwave background radiation. Here is the very first measurement by Penzias and Wilson. They simply asked themselves, how did the temperature of the sky vary as they pointed the telescope in different directions? A much more sophisticated experiment using the familiar technology of chopping led Partridge and Wilkinson to this upper bound in blue. Other upper bounds were appearing. One notices that many countries involved, here the Soviet Union, here, well, Green Bank, Australia, industry, an interesting time, oh, White Mountain. The interval, this is what was done between 65 and 79. Here, you see a grayscale that is what was obtained prior to the measurements on the present graph here prior to 1980. Only upper limits, but some getting pretty small. Here, is that you, Juan? They did the obvious thing, go to a telescope and measure, and pre-existing telescope. Yeah, others were building special purpose instruments, as in Wilkinson and Partridge. Relict, the first satellite measurement of the microwave background, detected the dipole anisotropy due to our motion and placed an important bound, but did not detect the microwave radiation. There were plans for Relic 2 that would have detected it, but the Soviet Union collapsed first. That's 1980 to 1989, 10 years of progress. Now, 90 to 93, oh, you should notice the vast change in scale. This is logarithmic. This is linear and much expanded. Top scale 700, much expanded again. Great progress. And detections. Here, the Kobe anisotropy experiment. Also detections here, max 3. And isn't there Saskatoon here in black? The first detections, as well as important upper limits previously obtained here on small angular scales. 94 to 96, Kobe had mapped out roughly the very large angular scale part of the spectrum, and we were starting to see evidence, first important upper bounds on small scales, a detection on large scales, and in between, clearly a rise. The anisotropy spectrum goes up and then comes down. Here, an interlude, as I point first to the state of the measurements, 97 to 99, showing pretty clear evidence of a peak. And at that time, the CDM model had become quite the vogue, accepted not only as the best working model, but actually as this is the way it is, which made me feel very uneasy, because at that time I could still think of lots of other ways to fit all that was known at the time. And I had set myself the goal of asking myself, can I fit these data in some other way? If I can, then it tells us that using this peak, for example, to constrain space curvature, is not good science, because you don't know that you have the right theory. You don't know you have the right theory until you have much tighter evidence than this. Here is a theory I made just as an alternative. It was a beauty. Perhaps you can read 3 scalar fields, one that drives power law inflation, one that survives, becomes present-day cold dark matter, and one that gives the cold dark matter field a mass that slowly varies during inflation. Bells and whistles, beautiful theory. And here are the predictions. If you compare point by point, I think you will find that my predictions more or less run through the data. No great surprise, I didn't publish until I had a theory that ran through the data. Lyman Page is quite convinced that I was also already blown out of the water. He points to his TOCO measurements here and here. They're both too high, but he says the relative amplitudes are reliable. And between 100 and 200, the measurements go up and I go down. Well, maybe. I mean, I think, in fact, I might have taken a 50-50 bet on my model working as well as lambda as CDM. But this is 97 to 99. The paper was published, I think, in 99, submitted in 98. Yeah, so I was safe then. But here's the next year, the year 2000. And now it is very clear. The spectrum goes up from 100 to 200, and I go down. So another beautiful theory gone. But one shouldn't stop there. Here there was by now great interest in the evidence that the measurements require small space curvature from the position of the peak. That made me uneasy because I didn't know whether I should trust the theory again. And in particular, I persuaded 2 bright young people, Sarah Seeger and Wayne Hu, to consider the possibility that at decoupling there was some source of ionizing radiation, a very modest amount, maybe decaying dark matter particles, who knows what. Let us postulate, instead of 0 space curvature, which is a postulate, that there is a source of ionizing radiation, very modest. That radiation is important only in that it tends to produce Lyman alpha resonance photons. Recombination to an excited level will leave you with a Lyman alpha photon that will rattle about. And that Lyman alpha photon will knock hydrogen in the ground level up to 2p, where it is easily photoionized by the radiation field until the universe is cooled more than the standard estimate. It's delayed recombination. That delay causes the distance between recombination and us to be decreased. That pushes the spectrum to larger angular scale, and so allows you to fit an open universe with low mass density to the position of the peak. Here it is demonstrated. Again, a theory of great beauty, but not well presented. And I think this is Wayne and Sarah's decision. Let's make the open CDM model as inconspicuous as possible. It is the dashed line. This is high, but that's okay. Not much constraint there. The dashed line goes way down. Do you see here? Pauses slightly and goes way up. Instead of 2 peaks of about equal size, there is this pronounced minimum and then maximum. Well, this is okay. Here's a minimum and here's a maximum. It would fit pretty well. An open universe would fit the peak as well as cosmologically flat. But the next year, give me a break. It's 2 peaks. It's not, our theory died. I must say I regret nothing. These theories had to be challenged. And I am impressed by the fact that they met the challenge with ease. Well, let's continue. 2003, it's being mapped out pretty well. And WMAP, you see, as before, I remind you, the shaded curves, shaded blocks, are what was established before this year. The spectrum was well mapped out. WMAP cleaned up some discrepancies. You see this is running high on large angular scales where it's very difficult to correct for emission from Earth if you're doing the experiment on the ground or in a balloon, and more tightly map these oscillations. That's the end of that series with a glorious fit of theory and observation, which, as you notice, we have demonstrated now is more than curve fitting. Curve fitting is involved. You have a curve that has a shape that may be adjusted by varying parameters. You, of course, adjust the curve to fit the data, but now you have, as you understand, a wealth of alternative constraints that show you that we are much more than curve fitting. So I come to my final topic. Shall I pause? I come to the final topic. Who put lambda in lambda CDM? So here is my reading of the situation. By 1999, I think 1999 is about the right date to say this, we had abundant evidence that the mass density in matter is small, maybe below 30% of total, from a variety of measurements. I'll just remind you of the situation in a little more detail. Here again, copies of old overhead view graphs. Mark Davis, the first systematic redshift survey. Mark Davis's handwriting, he hadn't yet put on the label in this one. My little squiggles. Here, the bright galaxies, here the faint galaxies, and I remember how he and I were so deeply impressed, it's hard to tell the difference. Bright galaxies, faint galaxies, they don't care. Notice how similar. Striking. These days, people often emphasize more luminous galaxies cluster more strongly. That's true when you get up to the CDs. It's not true at L star and fainter. And these galaxies are all L star and fainter. Here, big and little galaxies are distributed in the same way. That is not what you would expect in the biased theory that so grabbed the attention of people in the 1980s. Biasing requires that most of the mass is in the voids. Why in the world didn't that mass at least produce dwarf galaxies, irregular galaxies? Perhaps their formation suppressed somehow, but yet the survivability of a little galaxy in a void surely is high, much better than near a big galaxy. Why are the giants and dwarfs so similarly distributed? To me, it didn't make sense to invoke biasing as a way to account for the evidence from velocity dispersions, Virgocentric flow, that we live in a low-density universe. Others were convinced by other things. The APM galaxy survey gave an autocorrelation function that indicated a very low matter density if you accept a sensible value for Hubble's constant. Interestingly, George of Stadio at that time did not accept a low-density universe. Instead, he and others took the step of going, maybe some of you remember, tau CDM. You give me a problem, I'll invent a parameter. I remember accepting a big bet with Carlos Frank, a case of some fine beverage. If you find a cluster at redshift 1 with a velocity dispersion of 1,000 kilometers per second. But they were already there. Cluster mass, baryon mass fraction, very persuasive to Simon White. Well, by 1999, people had accepted the universe has a low matter density. Inflation had convinced many that the universe has to be cosmologically flat. The implication is you require a lambda. At that point, I think it is fair science to say this is an excellent working hypothesis, but you shouldn't be settling any bets because you haven't tested inflation. And in fact, you will recall that in those days we had open inflation, although people dislike to attach inflation to that. Rich Gott and others had open early universe physics that could plausibly account for the universe we live in. I think it's fair to say that the critical step took place in 1999 with 3 independent pieces of evidence for a cosmologically flat universe. The first, the product of stellar evolution age and Hubble constant, the evidence that it is not much less than unity. and with a mass density that we don't want to take less than maybe 20%, quite difficult to understand unless you put in a cosmological constant to speed up late time expansion, make H naught big then. I don't know whether 1999 is exactly the right age to say that this measurement gelled. Earlier, there were problems both with the extragalactic distance scale and with the stellar distance scale. By this time, these problems seem to be under control. I don't know whether this measurement alone would have convinced you that there is a cosmological constant. It certainly, though, was objective and good evidence. Same year, the redshift magnitude relation, and of course the CBR anisotropy spectrum, certainly with the distance scale, gave strong implications for a cosmologically flat universe. And you were starting to believe lambda CDM because of the exquisitely good fit to the anisotropy spectrum. Well, just briefly, let's remind ourselves that these measurements go a long way back, that Hubble and Tolman are standing in 1931 in front of a preliminary model for the great 200-inch telescope on Mount Palomar. That telescope is still producing useful data. Ask yourself, where are the particle accelerators of 1931? In museums. This is the nature of astronomy. The key project for this telescope, to use modern jargon, was to test cosmological models. 30 years later, the Hubble, the 21-centimeter telescope is in operation, and Sandage is saying it's time to use it for its original purpose, cosmological tests. The best way to do it, Alan said, is redshift magnitude relation. Here are data points, which you know mostly trace back to the 1930s. This was a slow period of slow development, but different cosmological models. Let's push forward to that. Well, here is how that research ended up, not with galaxies, but with supernovae. Two independent groups, each of which finding that the high redshift supernovae are slightly faint relative to what would be expected in an Einstein de Sitter universe. Strong evidence coupled with low mass density for lambda. So I come to the end, but I can't resist pointing out a few things. The great advance in the supernova measurements was recognized by a great prize. Here is Brian Schmidt, Adam Rees, and Saul Perlmutter holding a bundle of money. Here is Sir Run Run Shaw, deeply admired in Hong Kong and mainland China for his philanthropy. Founder of the prize. His suit fits him much better than their suits do. But nonetheless, they look much neater than I've ever before or since seen them. There are so many other people I could have mentioned. I didn't show you a photograph of Lemaitre. In 1930, he had the key. He best understood cosmology of anyone. I didn't mention the steady state theory, Fred Hoyle, Tommy Gold, who with Herman Bondi, were very important to cosmology for producing a new theory that so enraged the observers that they set to work to disprove it, and so advanced the subject. I didn't mention the puzzle of what in the world is this lambda, and the related puzzle, how the devil do we understand the energy density in the quantum vacuum? Pauli knew about that in the 1930s. Vera Rubin, rotation curves. I didn't mention 21-centimeter rotation curves as evidence for lambda. Zeldovich, who showed us that, boy, you better pay attention to the vacuum energy density. And, of course, my favorite picture of all time. It's been a remarkable advance. We are certainly not at the end. We have deep puzzles. How in the world do you understand that vacuum energy density? Do you truly understand the way galaxies are formed? But we have reached a sort of plateau where I think it's fair to say we now know that the universe expanded from a hot Big Bang, and that expansion is remarkably well described by Einstein's general relativity theory. And I don't have Einstein here. But it's a story of people at work and somehow making remarkable discoveries. Thank you.